Yeah, thanks for the nice introduction. I'm going to talk about 3 questions that typically come up at cocktail parties for me as a control theorist. So when I tell people at a cocktail party that I work in control theory, the first question that people ask is, like, what's control theory? And then the second question that comes up is, okay, so like, what does a control engineer actually do? In fact, at this airplane company, they actually were so unfamiliar with controls engineering that they misspelled the word controls engineer on my first business card. And I still have a stack of those business cards as sort of a reminder that this is not the kind of thing that everybody knows about and talks about. And then the third question, which we typically don't get to in cocktail parties, is what does controls research, like today at UCSB, actually look like? So that's what we're going to cover. So control theory is sort of best explained through this flowchart. The idea is that there are things in the real world that we want to control, whose behavior we want to influence in some way. And the canonical example is sort of a cruise controller for a car. You want to go at 70 miles an hour, but the wheel encoders on the car indicate to the car computer that you're only going 60 miles an hour. And so the controller, the car computer, sees those 2 numbers, and it uses the actuator, the gas pedal, to try to make the actual speed match the desired speed. So that's the whole idea behind controls engineering, is formalizing mathematically these 4 bubbles in a way that lets you actually compute with them and say interesting things about them. So I have a bunch of examples, just a few examples. So here's an inverted pendulum. The first control objective is to just invert the pendulum. So please just get it upright. It does this by pumping energy into the pendulum. And once it's stable, another controller kicks in, the goal of which is just keep it stable, even though these kids are like whacking it. And you know, then it can switch back and forth between the 2 controllers. So if it loses it, it can still go back into the energy pumping mode and get it all stable. Okay, let's see if this one works. Here's another inverted pendulum. This is a SpaceX test that happened about a year ago. The idea is maybe we can make space flight cheaper if we don't throw away the rockets after they get the thing up in the air. And so the whole idea here is, you know, this is just like an inverted pendulum. The beautiful thing about control theory is that it's the same math. You've got this big old rod that can tip over, and you have some actuation mechanism at the bottom for keeping it from tipping over. So that's the whole idea. So here we have these little flaps are going to pop out. They have, I think, a bunch of more sensors in them that can tell the you know, what the attitude of the rocket is. And then, as you can see, it's not going up in the air anymore. It's just slowly drifting down. But again, it's just like the regular inverted pendulum, in that the thing that's holding it up is you're pushing it from the bottom. So it's sort of an unstable system. Anyway, so yeah, so it comes back down to Earth. And what else interesting do I have to say about this? I love the cows down here. I'm sure this was intentional. The cows are freaking out. Yeah, and of course, they wouldn't have published this video on YouTube if the rocket did not come safely down to the ground. Okay, so this is just another inverted pendulum, and it's so awesome that the same math that you use for doing this in the lab can also be used to analyze the actual physical system of a big expensive piece of aerospace equipment. Here's another not inverted pendulum. This is a bunch of robots from a company called Kiva Systems that was bought by Amazon for like $250 million to move around the inventory in an Amazon warehouse. So the idea here is there's all these little white stickers on the floor, and each orange robot has a little camera on the bottom that is reading those stickers. The stickers have a QR code that indicate where in the warehouse it is, and there's a sort of a master computer in a closet somewhere that is taking the, is sensing where all the robots are on the floors. It has the knowledge of where the, what are the orders that need to be fulfilled, and so it moves, and so there's no humans in the interior of an Amazon.com warehouse. All the robots are trundling around carrying these things to the periphery where the humans are sitting there assembling the orders. So the thing that these 3 examples have in common is that this flowchart, obviously, because I keep talking about it. There's something that you want to control. There's some inventory in an Amazon.com warehouse that you want to move into a bunch of boxes that you want to move to the periphery of the warehouse. You have the ability to sense where the robots are in the warehouse. You have some controller in a closet that is coordinating the robots, and then physically moving them around so they can pick up the inventory and carry it, so on. So that's what control theory is all about. That's the high-level idea of what control theory is. Taking this flowchart, using some mathematical tools in control theory to analyze real-world systems, and then doing cool stuff in the real world with it. Okay, so how does a control engineer actually do that? This is the second cocktail party question. And I'll give you an example from that's close to my heart. It's the inverted pendulum, and this is something that every controls engineer has to deal with somehow. And in fact, on the 3rd floor of Harold Frank Hall, we have a controls lab where if you take ME 106 or ECE 147C, you will get, with your team of a couple other folks, you get a little cart here. You get this the little cart. So here's the track. There's a cart that has a rack and pinion, so this little gear is attached to a motor that can drive the cart back and forth. And there's, of course, the pendulum that you have to balance. And so there's wheel encoders. These are the sensors. There's the wheel encoder here that can measure where the cart is back and forth. And there's another wheel encoder here that can measure the angle of the pendulum. So if you take ECE 147C, which is happening right now, you will get to spend all your time being frustrated looking at this. And this is a Simulink diagram. So Simulink is a numerical block diagram solver that is part of MATLAB, which is something that we all engineers have to bathe in like for 4 years. And the whole idea is it can run real-time numerical simulations. And the cart systems come with a bunch of I/O, these blocks that you can actually interface with the real world. So under this cart system block, this cart system block takes an input U, which is the motor voltage that is assigned to the motor. So you're responsible for feeding in a stream of real numbers to this block, and it writes them as voltages to the motor. The output of the cart is the position and the angle of the cart. So that just reads it right from the wheel encoders. And we teach our kids in ECE 147C that this is a very common method of control design. It's called negative feedback control. So you're feeding back the actual cart in position and comparing it, subtracting it from the desired position and the desired angle. So here the desired angle of the pendulum is just 0 because you want it to stay upright, you want it to stay inverted. And the desired position of the cart, well, it could just be 0. That would mean it would just like stand here balancing it. But to make it a little spicier, we have the desired position be a square wave. So the idea is, please balance the pendulum like this, and now as fast as you can, please move over here and still be balancing the pendulum. And then go back and forth and back and forth. And so that's a little bit more exciting than just stand here balancing it, which is something that anyone could do. So this is the desired position and angle. You subtract from that the actual position and angle, and then there's some sort of error, right? This is just like a cruise controller in a car. I want to be going 70 miles an hour. I'm actually going 60 miles an hour. There's a 10-mile-an-hour error. Do something with that. The controller's job is to do something with that number, with that stream of 2 numbers, the error in position, the error in angle, and from that stream of numbers, come up with the motor input that goes to the cart. Okay, so the whole 10 weeks of the ECE 147C, the students are learning about what goes in this box here. And here's how they figure that out. So the first step, so here are a couple of slides from one of the students' final presentations from last year. The first step is draw a free body diagram. And sorry, this box doesn't seem to be showing up here, but trust me, this is a box that's supposed to represent the cart. And so there's like all like the gravity force on the cart. There's a bunch of reaction forces from the pendulum on the cart. And here's the pendulum. Here's the the mg of the pendulum and the other reaction forces. This is just Newton's second law. F equals ma. This is for F equals ma for the position of the cart. This is p, the position of the cart. So p double dot is the acceleration of the cart. And this is F equals ma for rotations. Sum of the torques on the pendulum equals I alpha. Okay. So this is just first year physics, and then these forces here just come from physics and geometry. So for instance, this is the voltage that is being applied to the motor. This is the resistance in ohms of the motor windings, and so V over R is a current. The current is proportional to the force on the cart, because it's like proportional to the magnetic field that you're producing in the motor. So, okay, so this just comes from physics, and there's a bunch of geometry in here. So the kids derive all this stuff, and they plug these things, into the F equals ma, and they get these 2 equations, which are 2 nonlinear differential equations that depend on things like the motor voltage that you're applying to the cart. So, okay, these are big ugly things, and we teach the students in 147C a technique called linearization, where they linearize this big ugly system around this sort of unstable equilibrium point of the balanced pendulum, and they boil this big old thing down to 2 equations that look like this. So 2 linear first order vector differential equations. The vector here, the state x, the state vector, is just the position and velocity of the cart, the angle and angular velocity of the pendulum. Okay, so that sort of fully describes the state of the system. Is it like freaking out over here, or is it perfectly balanced, or what? And so once they've done this technique called linearization, these are just constant matrices, and the students use another technique that we teach them called system identification for figuring out what exactly are the numeric values of these 4 matrices. Then, so once they've got this is great news for the students because they have boiled this big complicated system down into a very simple canonical form that describes the motion of their system. Once they've done that, we teach them about a very simple control design called state feedback control. So this U here is the motor voltage that you're applying to the system. Kind of sucks that we have a V up here and then a U here, but that's sort of, we have to deal with the notation. In state feedback control, the motor voltage is just some constant matrix times the state vector. So the state vector is a 4×1 vector, and this is a scalar, so this is just a 1×4 row vector. You're essentially doing a dot product between the state vector and this thing k that you get to choose. And what the students have to choose with k is, let's see, if you plug in u equals kx into this equation, then you get ax plus b kx. You pull out the x, you get a plus bk times x. So this, with this control law, this is how the state vector will evolve. And if you can pick a plus bk so that it has negative real part eigenvalues, in other words, just for imagine for a moment that this is just a scalar equation, and you would have something like x dot equals minus x. Okay, well that's like, the solution to that is like e to the minus t. It's like a decaying exponential. And so if you can arrange, so in the matrix version of that, it's the same idea. Instead of -1 here, you just want this matrix to have negative real part eigenvalues. And so if you can arrange for that to happen, if you can pick a k so that a plus bk has negative real part eigenvalues, then this control law will make it so that the state decays to 0. So that the position will go to 0, the cart will go to 0, the velocity of the cart will go to 0, the angle will be 0, the angular velocity will be 0, life will be great. So the students then have to worry, how do I find this k? And the great news is we tell them. We tell them how to find the k, and under certain conditions, you can pick a k that makes these eigenvalues as negative as you want. So you can make the system as snappy as you want up until like the nonlinearities like noise and stuff creep in. Okay, so that is how the control engineer, that's the behind the curtain, that's how the controls engineer does it. And there's a lot of other methods for how to design a controller. This is just a very simple one, a state feedback controller using negative feedback. And I've glossed over one detail, which is, well, wait a sec, if you drive x to 0, then aren't you just holding it right here? And well, I thought you wanted to move it in a square wave. Well, don't worry, because there's a very simple extension that, that allows you, instead of driving x to 0, driving x to some reference. And so here the reference would be this square wave that we're talking about. So here's yours truly in the controls lab on the 3rd floor of Harold Frank Hall, running the simulation. And of course, and it's not as cool as the first one because we don't swing it up. We let the students just start it already vertical. But every 10 seconds or so, it gets the next step of the square wave, and then it has to jerk around so that it moves the pendulum over. So it's going to jerk around in a second here. Okay, wow, there it goes. This is like the highlight of ECE 147C. So I hope you're all as excited. This lab has a special place in my heart because this is the lab where in 2006, as an undergrad here, I got really excited about control theory. This is the first time that I got to do something real with real control theory. And by the way, there's something really special about this. So, okay, you see that when the pendulum wants to move from the left to the right, when it wants to move right, it can't just move right because the pendulum will tip over the wrong way. It first has to go in the other direction. See how it sort of jerks this way and then it can go this way? It has to move. If it wants to go over here, it has to first go in the opposite direction to get the pendulum falling, and then it can go and pick it up. So nowhere do the students explicitly write in MATLAB, if you want to move the pendulum to the right, you first have to move it to the left so that you get the pendulum falling and then you can move it over. Like, you don't have to explicitly say that. You just get that for free from the math. Like, that just falls out of the dynamics in the control theory. And I think that is so cool. So that's what a control engineer does. Okay. The last thing is, what does real controls engineer research look like that is happening today at UCSB? And I have 2 examples. And the 2 people who do the research are actually here in the audience. So if you have specific questions about it, I can just ask them. The first one is from David Kopp, who is right here. And he works in, he has developed a combination of 2 well-studied controls problems and combined them into one. And the idea, and so here, I don't know if you guys saw the grad slam, but David participated in the grad slam and got to the finals and everything, and it was very cool. And this is one of his slides from the grad slam. The idea is, if you have type 1 diabetes, you aren't very good at regulating your blood glucose level. So instead, a sensor will measure it for you, and an insulin pump will receive those measurements and figure out how to pump insulin into your body in order to keep your blood glucose level at an acceptable level. And so what David does is he has an algorithm that is not a simple state feedback algorithm, because a simple state feedback algorithm, if you remember the pendulum, that thing would waggle all over the place before it would sort of end up at its final value. And you can't possibly do that with blood glucose level. There is a hard constraint. You must not drive the blood glucose level down too low, or the patient will go into a diabetic coma. So David has a different kind of controller, and every 5 minutes it computes 45 minutes into the future. It says, what is the best insulin trajectory that I should assign for the next 45 minutes in order to bring the blood glucose level down as fast as possible, subject to the constraint that it does not bring it too low, that it does not bring it into the coma level. And then it executes that plan for the next 5 minutes. So the remaining 40 minutes of that plan, it then discards, and it recomputes the entire optimization another 45 minutes into the future. So this is a technique called model predictive control, because he's using the model of the human body to predict what the blood glucose level will do as a function of some sort of optimal insulin trajectory. Anyway, so that's what David does, and I think that's very cool. Okay, here's the last example, and then we're done with time to spare. So Stephen Quintero is a recent graduate of our lab, and he works on UAV routing. So the idea here is there's a truck. The truck maybe has a bad guy in it, and you want to know where the truck is as he's trying to drive away. And you have a couple of airplanes, these unmanned aerial vehicles, UAVs, that have onboard cameras. So they're flying around, subject to the constraints that they're an airplane, they can't just hover in the middle of the sky. They're flying around, watching this truck, and relaying their information, their position from GPS and the camera, the camera frames, to a command and control computer. And based on what that computer sees from the UAVs, the computer's job is to route the UAVs to try to follow the truck and figure out as precisely as possible where is the truck. Okay, so what people thought in the past, which was a reasonable thing to think, is that, well, each UAV can see pretty well from side to side, but it can't determine depth very well. So here's, for this red UAV, there's this uncertainty ellipse, of where the truck is. The red UAV can tell from side to side pretty well where the truck is, but it can't tell depth very well. So why don't we just have another UAV that is looking sort of 90 degrees away from this one, and that one will be able to resolve in this direction really well, which was the poor direction of this guy, of the red one, and so that the combined uncertainty will be this pink, this sort of purpley pink uncertainty ellipse. And so this is called standoff tracking, and the idea is we'll have the UAVs at 90 degree angle, and that'll sort of minimize the combined uncertainty. The problem with that is that the UAVs cannot magically track at 90 degrees, and follow this truck wherever it goes. They're subject to the movement of, these are called non-holonomic vehicles. They can't just move however they want. They're subject to certain flight constraints. And so what Stephen did was he, instead of trying to keep them at 90 degrees, arranged an optimization problem where the goal of the optimization problem is not keep them at 90 degrees, but minimize the size of this combined uncertainty ellipse, of this pink ellipse here. So here's an example of his algorithm running. This is, the truck is sort of randomly moving and driving and so on, and the UAVs, you can see, are not staying at 90 degrees at all. It sort of looks more like they're taking turns swooping over the target. Now, Stephen did not explicitly say in his code, please swoop over the target, alternate and swoop over the target. That was just the result of his optimization, which aims to minimize the size of the combined uncertainty ellipse. So what this looks like in the whole, this is the whole flight. Here's the little truck driving around, and you can see that the UAVs are not doing a very good job at staying at 90 degrees. They're just kind of swooping over the truck in accordance with the solution of this optimization problem. So here is the Here is the average size of the uncertainty ellipse. This is the distance of each UAV to the target. And so you can see here that they really are sort of taking turns swooping in over the target. So it really seems like the optimal thing to be doing is trying to keep, on average, trying to keep the UAVs as close to the target, as above the target as possible. And then this is the most important graph, because this is the angle between the two UAVs. If Stephen's optimization problem aimed to keep them at 90-degree standoff tracking, you would expect this pink line would be very close to 90 degrees the whole time. But instead, it is wildly deviating from 90 degrees. And this sort of the big takeaway from this project that Stephen did was that 90-degree standoff tracking is not the best thing that you can do. If you can spare the computational horsepower, you should be running an optimization algorithm that directly minimizes the size of the ellipse, not tries to keep them at 90 degrees. So that's another example of real-world controls engineering that is happening right now. So that's the end. What is control theory? It's this little blue flow chart. We're trying to control the behavior of the world by analyzing it using math. What does a controls engineer do? Well, it's kind of like a lot of physics, and then you use, of course, the tools of control theory to sort of regulate that physics. And then what does research look like? Well, it's like using those tools to regulate people's blood glucose levels, or keeping the good localization of where the truck is. Okay, thanks very much. Thanks.
Does anyone have any questions for him?
What kind of projects, other than what you shared, have you done?
Oh, my work is kind of boring compared to these guys, but it's called like limited bandwidth control. So remember this negative feedback control loop that with the pendulum. The assumption in the theory, the undergrad theory, is that you have a continuous stream of infinite precision real numbers that are being fed back to a controller. And that makes life easy because you can analyze it nicely that way. But in reality, you do not have an infinitely fast stream of them, and you don't have infinite precision. So you have bandwidth limitations, and that's sort of the study. That's my work, is how can you extend the theory to accommodate limited bandwidth. Does that make sense? Yeah. It's we don't have anything as cool as airplanes or bodies. Yeah, it's just theory. Stephen?
Yeah.
What?
No, I just wanted to ask with your inverted pendulum example. What did you measure? Do you have all the states measured in your state feedback controller?
Okay, yeah, thanks for asking.
How do you resolve that if you don't?
Yeah, so Stephen is very cleverly pointing out that the volume is turned up. Stephen's very cleverly pointing out that there are only two measurements of the inverted pendulum. We know where the cart is because we have a wheel encoder, and we know what the angle of the pendulum because we have another encoder. And we are not measuring the other two states, the velocity of the cart and the angular velocity of the pendulum. We don't have sensors that are directly measuring those things. And so you cannot, so I glossed over this in the interest of time, you cannot directly use state feedback because you just don't have all of those four things being measured. But instead, we teach the students in EC 147C another technique called, they build what's called an observer. And this object is a mathematical object that uses the knowledge of the things that you are measuring, the position of the cart and the angle of the pendulum, and the knowledge of the dynamics. So it sort of simulates, there's sort of an internal simulation of the pendulum inside the controller that, based on that internal simulation, can determine the derivatives of those things. You could, I mean, if you want just the derivatives and you're not measuring the derivatives, but you are measuring the things, the integrals of the derivatives, you could just like differentiate those things, but that leads to much poorer performance than if you have an internal observer. Yeah. You probably knew that though. Yeah, thank you. Yeah. Thanks.